Soumitra sir.
Can you hear me?
Yes, sir. We can hear you.
Okay.
Yeah.
Thank you, sir. Thank you, sir.
Okay.
We are starting.
Okay, we'll start.
Yeah, start, madam, please.
Good evening, everybody. Welcome to day 2 of our ATAL-FDP program. So today, the first speaker is Professor Soumitra Satpathy. Professor Soumitra Satpathy is Professor of Physics and Head, Center for Sustainable Energy at IIT Roorkee. A pioneer in solar energy research, Professor Satpathy is best known for his work on high perovskite solar cells. It is believed that these perovskite solar cells can be a game changer for next generation low-cost solar cells. He has published more than 150 high-impact research papers on solar cells and filed several patents. Professor Satpathy is an elected fellow of Australian Institute of Physics UK, Royal Society of Chemistry, Energy Institute UK, to name a few. He is the founding president of Perovskite Society of India. He is the member of different committees of Government of India and serves as expert member in several ministries. In his long research journey, Professor Satpathy has guided several PhD students, postdocs, and master's students. His startup, Perovskite Innovation Private Limited, is India's first indigenous perovskite solar cell manufacturing company. Professor Satpathy has received several national and international awards in recognition of his pioneer work, including Fulbright Faculty Fellow, Outstanding Faculty Fellow from IIT Roorkee, DRDO Scientist Award, Bhaskara Award, Government of India in Solar Energy Research Award, GCRF Award from University of Strathclyde, UK, Directors Award from Max Planck Society, Germany, and Indo-Canada Shastri Award from Shastri Institute, Canada. He is also an active TEDx speaker. We welcome you, sir.
Yeah. Thank you very much for your kind introduction.
Thank
Am
you.
I audible?
Yes, sir. You are audible.
So you can check your slides screen.
Yes. I'll just check my slides. Okay, my screen is visible?
Yes, sir.
Yeah,
Yes.
visible.
Maybe for the bandwidth problem, I'm just switching off the video. Okay, so
Okay.
I think just let me try to do the full screen.
Yes, sir.
It's visible, right?
Yes, sir. It's visible.
Yeah, just this one.
Yes, sir. It's visible, sir.
Okay. Good. So very good evening to all of you. Hope that this today's evening with a cup of tea might be a journey for energy for all of you. And first of all, I like to thank Dr. Ravi from IIIT Kottayam for his very kind invitations. It was really pleasure, to be here with all of you today. And I really like to thank him for giving this opportunity to talk here. Yeah. So today, I know this FDP program is on AI and emerging technologies for sustainable energy and climate adaptations. I'll tell you about a story about a new technology, new emergent technology on the sustainable energy field, that is the perovskite solar cells technology. And also I will explain that, how AI and ML can be useful to utilize the maximum benefits of these photovoltaic modules. Now, before we go for this, we need to first understand the basic properties of the material, basic properties of the devices, some fundamental knowledge of the optical and electrical properties of these photovoltaic devices. And then we can discuss about how the AI and ML algorithm can be used for this particular purpose. Okay. So before I start my whatever I want to share with you today, I like to introduce that about my campus. I am also from is one of this IIT. I mean, you guys have 3I, but I have 2I in my institution. So it is Indian Institute of Technology. So I belong to the very close part of the Himalaya. So it is one of the it is the oldest engineering college in Asia. And initially it was Thomson College of Engineering. Then later on it was University of Roorkee, and then it turned out to IIT Roorkee. So we have so consistently this campus has been ranked as the most environmental friendly and beautiful campus in the country. So I like to invite all the participants and host, if you get a chance to visit the campus and just enjoy the beauty and serenity of Himalaya. So as I always say that, staying in such a place where you can get so much of sunshine in the bank of Ganga and in the Himalaya, it always inspires us to work something how we can utilize this solar power to something very useful form of energy. Okay, so I like to also since this is an FDP program, I also like to invite all of you about, I also want to take your attention to one important book written by David Goodstein. The name of this book is Out of Gas. It's very, very relevant in present context, where there are maximum war or maximum fight in the world is going on for the natural gas or petroleum or diesel. Now, this book has talked about what will happen, when the age of the oil will come to an end. So this basically tells you the dependence of the fossil fuels on our modern civilizations, and how and why it is extremely important to come across an alternative solution of renewable energy and advanced photovoltaic materials for the existence of the human being. Now, the photo in the right hand side, it shows you that a polar bear, it is struggling in the water. There's a piece of snow in the Iceland where the most of the ice has been melted due to the global climate change. And then this guy is who needs the ice for his existence, it's very hard for him to survive, and only there is a piece of the snow is existing, and very soon it will also be melted. So although the International Panel on Climate Change, IPCC, estimates that the global average sea level will rise by 2 feet in the next century. Okay, so that means that many of the continents and many of the countries, they will be under the water. So this simple picture of the polar bear is a very, very alarming situation for the humankind. So unless until we take an immediate measure on to protect our climate, to find out the renewable energy by adapting different means, so then it will be very, very difficult for human being to progress and move forward. So ultimately, the energy that matters. Even now I am giving this FDP talk sitting in the Roorkee, Haridwar, north part of India, and you guys are sitting in the Kerala, the south part of the country. So this communication is being possible through the laptop and through the internet systems, and then even the topic the AI and ML in the photovoltaics and climate adaptation. So when you want to use on the AI or ML techniques, so you need to run your code in some very high CPU, high memory computer. So for every case, if you want to run any single instruments, basically you need electricity. And so without electricity, you cannot we cannot have this FDP program actually, this talk cannot happen. Without electricity, you cannot do any AI or ML. So the first thing is that from the morning to night, what we need is the electricity. And the electricity comes by burning the fossil fuels. So the sources are natural gas or coal or petroleum. So eventually, that's why whatever the technology it comes, whether it's a space technology, defense technology, or medical technology, quantum technology, AI, ML, finally, every technology at the heart of it is the energy. You need electricity, you need energy, then everything is possible. So, and whenever you want to generate energy, let's say I wanted to install 10 more, nodes for my AI, ML work, or I want to do for my DFT simulation work, whereby I need a supercomputer of high speed. So basically, what I am increasing, I am multiplexing the expenditure of the energy. So that means the production of the electricity requires more, and production of electricity means more carbon dioxide emission. More carbon dioxide emissions mean global climate change. So these things are all interlinked. So that's why, it is very, very important first how we can find out some alternate source of energy apart from the existing electrical energy. Now, like other countries, as you know, that India government is very, very proactive on renewable energy research. And just like, the government has given a lot of importance on the space mission, government has given a lot of importance on the quantum mission, semiconductor mission, AI and ML technology. At the same time, government has given huge importance on the renewable energy technology. So by 2030, as you can see here, the renewable energy installed capacity target is 10 terawatt, where in 2021, the capacity is 3.1 terawatt. So there is a significant jump is required. Now, out of all these different types of renewable energy, basically, there are solar energy is there, then there are wind energy is there, then there is you have this biomass energy, then you have tidal energy. There are different sources of alternative energy is there. But out of all of these, solar energy is very, very promising. First of all, it's a very neat and clean source of energy. The amount of the carbon emission happens here, so that is much less in comparison to the other technology. For example, you guys are also heard about recently about green hydrogen emission. So there are a lot of people want to work on green hydrogen. But when so the meaning of the green hydrogen is that the generation of the hydrogen, the electricity which is required for water electrolysis, that should come from renewables. So that means it's the solar. And solar is still dominates the renewable energy market in the country and in the abroad also. So the currently, in by this November 2024, in our country, we have installed a solar power capacity of 90 gigawatt. And I must mention that the government of India wants to put a target of an installation of 500 gigawatt by 2030. This is actually in the line with the government's plans of becoming a net zero carbon emitter by 2070. So India want to become a net zero carbon emission country. So we wanted to work for the climate change. So one of the way the climate change can be can be worked upon is by working on the reduction of carbon emission. So is the total output of the carbon emission minus the total input carbon emission is zero, then which is very, very hypothetical in sense, then it is then we call it as a net zero, and the target is by 2070 the government wants to the India wants to become a net zero country. Now this out of this 500 gigawatt of renewable energy which is targeted in 2030, which is our target of solar energy, 500 gigawatt. So right now still we are much away from our target. So there are multiple reasons behind that why we are not still far away from our target. First of all, in our country, when we talk about photovoltaics, the first thing which comes in our mind is the silicon solar cell. Now, if you ever wonder that where this silicon solar cell comes from, all the module you see in the building rooftop, all the module you see in the school or college hostel, or in various industrial setup. So where this solar panel comes up basically. So if you look at a solar panel, you can see that these are made out of a lot of tiny small solar cells. Now these cells are assembled together in a big module, and that module basically assembled further together to get a panel. Now, India as a country, we never manufacture these silicon solar cells. We import them from the outside country. We import them from Thailand and China and some Germany and some other country, especially like from the China. Now, since it is import driven, so that's why all we do here is that by importing the cells, we just assemble them to make a module. But if we want to meet a target of 500 gigawatt of solar power by 2030, let's say, and if you wanted to be a net zero economy, if you wanted to fight for the climate adaptations by promoting photovoltaics technology, renewable energy technology, then we must be self-reliant in the manufacturing of our silicon solar cells. So that's why the government has started several schemes so that the silicon solar cells manufacturing facility can be established in our country. And there are various big companies which were the main player in the solar industry. They have started fabricating, manufacturing the cells in the country. Okay, and that has created lots of job opportunity, lots of technology development, lot of R&D, etc., etc. Now, one of the things is that this once you wanted to increase the number of the solar panel to meet your target of 500 gigawatt, obviously you can make, if you are making today 100 silicon solar cells, tomorrow you have to make thousands to meet a target of 500 gigawatt. Another way of achieving it is that how we can improve the efficiency of the solar panel so that the less number of panel can do the same job. For example, if you have a solar panel of efficiency 15%, so probably you need thousands of solar panel to get a power of 100 kilowatt. But if you have an efficiency of 25%, the same power can be achieved by much less number of panel, maybe 50 or 60 number of panel. So if the cost of the production of this high efficiency panel is almost similar or even less than your silicon solar cell production cost, then this is a remarkable technology and our country needs this kind of technology. Now, India is a solar-based country, although we have patches of solar radiation for places like Rajasthan, which needs a lot of sunshine, most of the year, most of the places of the state. But several other states, they have also some good area where, you get a good sunshine over the different time of the year. But also there are places where we get a very diffuse solar radiations. So another challenge is that whatever the solar cells or photovoltaic technology we will be developing, that will be able to work in the diverse climatic condition of the country. Okay, so for example, if you go to mountain or hilly area where you don't get a proper angle for the solar panel installations, or mostly if you get a cloudy weather, then you don't get a maximum efficiency from this panel. So your new panel or new devices, photovoltaic devices, should be working also under the diffused light or diffused radiation. That is one of the major challenge in the photovoltaic technology now. How we can develop a new solar panel which can even work under low light, even diffuse sunlight. Okay, so these are some of the challenges which is right now in front of us. And as I have just mentioned here that the government's target is to go from 1 lakh megawatt to to have this much about installed solar capacity by 2025 from around 3000 megawatt presently. And there is a huge amount of investment coming in the field, but we don't have that kind of manufacturing facility. We don't have the new technology which can cater this need. Now, how to solve it from a from a scientist point of view, from an engineer point of view, or from a technologist point of view? So obviously, then the science said that if you look at any photovoltaics technology, any renewable energy technology, for example, solar cells, obviously, so then the solar cells is made out of the silicon, and silicon is a semiconductor. And you know that that the first silicon solar cells was made way back in 60s. So it took almost 40 to 50 years for the solar cell technology to come to the present status. Just like in mobile, you have the different generation, you buy the different generations of the mobile. Similarly, in photovoltaic technology also, you have first generation, second generation, and third generation solar cell. First generation solar cell is basically your silicon solar cell, which is like, which is a polycrystalline silicon solar cell, but and single crystalline silicon solar cell. Then you go to like, second generation solar cell. So that is basically a new types of semiconductor called cadmium telluride, which is also called a quantum dot, CIGS, or kestrite materials, and multicrystalline silicon solar cells. But thanks to the discovery of the new materials, then we have this third generation solar cell, which includes this dye-sensitized solar cells. Kerala is doing a lot of good work. Like, there are certain labs, NIST Thiruvananthapuram in Kerala, doing a lot of good work on dye-sensitized solar cells. And then there are organic solar cells is there. There are some labs, for example, IIT Kanpur is doing fantastic work on organic solar cells. Quantum dot solar cells, like, and also perovskite based solar cells, like, which is a very new advanced technology, which has the promise of breaking all the records so far. Now, obviously, like, if we go from like, one material to another material, we have so many materials. So then there is a combination of so many materials is there. So there is a combination of their, like, their band gap. Is a combination of their optical properties, optical absorptions, their emissions, their electrical conductivity, their mobility, their charge transport diffusion length, right? So if you look at a molecular level, so if you have so many variations of that, then how we can optimize so many variations to see a solar cell with a maximum efficiency and a maximum stability. There, your role of the AI and ML, artificial intelligence and machine learning comes. So in a nutshell, basically what AI or ML does, like, they handles the big data. So you input a big data first, and then you divide the data into different portions, like, in a standard way. Like, the first set of data, which is usually large percentage of your total population, you put it as a training set. And then, like, once you train it using some existing algorithm or model, then you actually instruct the system, like, how to read or how to follow the particular instruction which you have fed. Now, that particular instructions or informations can be the band gap of the material. It can be the, like, optical parameters of the material. It can be like, electrical parameters like dielectric constants, or like, polarizability, or anything, like, what you want to put it. And you might have to like, consider this fact also, that a solar cell is basically a multi-stacked structure. It is not a single material, right? So if you look at a device, so it's a multi-component material. Any solar cell has three primary components. One at the center, which is called the active layer, which basically absorbs the light and converts the light into the electrons and holes. And you separate the electron and hole in the external circuit, and you get a current. Now, to separate the electrons and hole, you need to put the bias. You need to provide some voltage difference. So that's why we put two electrodes, one on the top and one on the bottom. One called is anode, another is called the cathode. Now, to improve the efficiency of the process, like, we put also some another material between cathode, anode, and the active materials. For the case of the silicon solar cell, your active material is silicon. And now, if you are working on a quantum dot solar cell, your active material will be quantum dot. If you are working on an organic solar cell, your active material will be organic material. So basically, you are just changing your active material, and you are changing the different types of solar cell. In a perovskite solar cell, your active material is perovskite semiconductor. Now, apart from the active layer and these two metal electrode, we also put different organic and inorganic layers in between the metal electrodes and the active layers. This helps for the charge transport and the charge extractions. We'll come to know about in details later on. But as I mentioned, like, we are right now in a third generation, or some people also claim that we are in the like, photovoltaic technology 4.0. So 4.0 is basically is a new types of technology, like third generation solar cell technology, integrated with some like, with some second generation technology or some new advanced technology. For example, like, perovskite solar cell, which is a third generation technology. Now, if you integrate it with the first generation silicon solar cell, you get a silicon perovskite tandem solar cell, and you call it as a fourth generation or photovoltaic technology 4.0. Now, why this particular topic we have chosen today, or why this particular topic we are working on, like, what is this perovskite? And so we'll come to it will very soon. But for right now, for the information, like perovskite solar cell, which is a new entry in the market, holds a lot of promise than the conventional all other technologies. And just to mention that, that what is the efficiency of a silicon solar cell? In a module, polycrystalline module, it is 15%. If it is a monocrystalline module, it is 20 to 21%. But a perovskite solar module have an efficiency of somewhat very close to 25 to 26%. And this remarkable improvement in the efficiency has been possible by doing an R&D for only last 10 to 15 years. It has been started in 2009 and now it is 2024. So 15 years of research, and now the efficiency is somewhat around 25 to 26%, and this number is increasing every day. It has been possible by doing an exponential amount of research about the material properties, material optimizations, device properties, device optimizations, which is backed up by the theoretical study and also the artificial intelligence and machine learning based predictions. Now, coming to the next slide, obviously, which naturally comes to your mind is that why perovskite solar cell technology? What is so much big thing about that? If you compare to the amorphous silicon solar cell, basically, the first thing I mentioned you that for the perovskite solar cell, unlike amorphous silicon solar cell, the performance under the low light is also very high. If you take a highly efficient crystalline silicon solar cell, the performance under the low light is low, but for a perovskite solar cell, it is very high. And power to cost ratio, any technology will only be feasible if its cost is also low. Power to cost ratio for the perovskite is also 1/4 of the silicon technology. And another thing is that you can make this solar cell in a flexible form. So that means you can bend it, you can stretch it, you can walk on it, you can jump on it. So that means you can put these solar panels either on some kind of wall roof, you can put it on your bag, you put it on a tent for the defense application or for any other space applications. And these solar cells are ultra lightweight. They are very, very low weight. So one can literally carry kilograms of the or some high weight of the solar panels easily without any problem. Now, even also one data I just wanted to draw your attention that the market size of this solar cell is also increasing in a very significant way. So it is while in 2021 it is only 0.60 USD, it is expected to hit around USD 7.2 billion by 2030 with a composite growth rate, CAGR rate of 31.8%. Now, what is CAGR rate? For some of you information, for any new technology or any old technology, basically how good the technology is doing, what is its growth rate? So this has been quantitatively, it has been measured by a quantity called CAGR, which tells you the composite annual growth rate of a technology. A composite annual growth rate of more than 10% for any new technology is always a fantastic news. But here the perovskite has a CAGR rate of 31.8%. That's the reason there are so many companies over the world. I am showing some of them: Oxford Photovoltaics, Solid Technology, Toshiba, Panasonic. They are all making gigawatt scales perovskite solar panels. Perovskite based solar cells is there. And in India also, although we have started a little bit late, but we have picked it up very quickly. We don't want it to also be in the back in the race, so that that in the case of silicon solar cell, in the beginning I mentioned that still in the country, there are many places is there where there is no electricity is there. There are many places is there where there cannot be any industry because of the lack of the electricity. But if we can use the solar panel or any other alternative technology, so this problem could have been solved. But it is not possible a very, very overhaul overnight, because we have a limitation of the supply of the solar panel, because we don't make the cells here. We import the cells, and as I mentioned, we assemble them to a panel here, and we sell the panel, not the cells. If you wanted to be in indigenous manufacturing in the silicon solar cells, then we can make our own cells, and then we can sell it, make our own modules, and then we can make our purpose. So now here is a technology which you can ingeniously make in our country, and also which beats silicon in various ways. It has a high efficiency, it has a free form factor, etc. So there's a huge potential right now for a new upcoming technology, to replace the existing silicon, or working with the silicon to make a silicon perovskite tandem solar cell bed technology. Now, although I'm talking from the beginning, this perovskite solar cell, the first thing, it might come to your mind, what is this? What is perovskite? How it is pronounced? I mean, so why you are calling it as a perovskite? So basically, perovskite is nothing but a semiconductor. Just silicon is a semiconductor, germanium is a semiconductor, right? Indium gallium arsenide is a semiconductor. So similarly, perovskite is a semiconductor. And it was first discovered in Russia in 1839. And the person who first identified its crystal structure, his name was Lev Perovsky. So his name was Lev Perovsky, who is also a Russian person. So since according to his name Perovsky, this material was given the name perovskite. Okay, and this is a semiconductor which is available in a plenty of amount in the Earth's mantle. And this particular semiconductor has a crystal structure called ABX3. Now, what is ABX3? I mean, in this crystal structure, your if we have a photo, it will be much better to visually see this thing. You see, this is, I have drawn a cube, basically a nice three-dimensional cube. And in this cube, at the body center, there is a black color ball is there. And in the body center, this black color ball of this semiconductor, it is usually a metal or divalent metal. For example, lead or tin or bismuth or germanium. So these kinds of metals are there, in the center of these things. Now, at the face center, you can see a large blue color ball, right? So these are the halide ions. Halide means chlorine, bromine, and iodine. And at the corner of each and every square side, you can see there are some reddish or some olive color, small marbles are there, and these are basically cations, organic or inorganic cations. So these are the composition of this material. So this material has a metal cation at the face center, and then at the body center, and then there are blue colored your halide ions at the face center, and at the corner of each and every corner you have this organic or inorganic cations. Now, if the center this metal cation, that you call as an X, that you call as a B. So the B is the cation at the body center, and this red color marble, that is A, that is the corner at the that is the cation at the corner of the cube. And this blue color larger ball, so that is the halide ion at the face center. So you have three things. One, I am calling it as A, which is a general name. A can be any cation. It can be as I mentioned that it can be any cation. It can be an organic cation. It can be an inorganic cation. It can be a combination of organic cations. It can be a combination of organic and inorganic also. Similarly, B, that can be a cation at body center. So for example, it can be lead or tin or germanium or bismuth or antimony or anything, right? Which has a valency of 2+. So in the periodic table. And then there are halide, chlorine, bromine, iodine. So now the interesting thing about this particular structure is that now you have this cube. Now, what you do, let's say you imagine a three-dimensional space where each of this corner, each of this olive color, corner, they are shared by one of this cube. So basically at each of this corner, you have one more cube. Here, there's a one more cube. Here is a cube. Here is a cube. Here is a cube. Here, and here. So basically there are 4 plus 4, 8 cube, which have been covered this from the all directions. So what you get, basically, you get a cubo-octahedral volume, a large gigantic structure, cubo-octahedral volume. And this structure is called the perovskite crystal structure. And this is the structure that makes this material so interesting. Why it is so interesting? First of all, this kind of structure gives a very large carrier diffusion length. What is the carrier diffusion length? For example, I have a material, I shine the light on it. You generate electrons and holes in it. Now, what will do the electrons and hole? They will recombine with each other. If they recombine with each other, then I don't get anything in the outside circuit. So what I want the electron to go in one direction and hole to go to other direction. I want to separate them, not recombine them. So that's why the electrons and holes that has to travel to the metal electrode before they recombine with each other. Now the distance they can travel before they recombine, that is called the diffusion length. Now you can see that the diffusion length of the perovskite is 100 nanometer to 1 micron. So it's very long. That means in perovskite semiconductor, if an electrons and hole generates, so they can move until 1 micrometer before they will recombine with each other. And even nowadays, it has been proven that it can even go to 100 or 200 micrometers, 500 micrometers. So that is the reason, this material is so much good conductive of electricity. Second thing is that it has a very high dielectric constant. Now, what is the role of the dielectric constant? You know that dielectric constant is related to the binding energy, right? So if your dielectric constant is high, so the Coulomb potential between electrons and hole will be less as per the basic electrodynamics. If you have read the basic electricity magnetism, you know that Maxwell's equation, the first law is called the Gauss's law. What it says that the attraction between the electrons and holes, the force, so that is actually depends on the dielectric constant. So if the dielectric constant is very, very high, so then the binding energy will be low. If the binding energy is low, that means electrons and hole, they cannot combine with each other. They remain free. You want them to be remain free so that you can collect them in the outside web. So that is another benefit here. Okay. And another thing is that this material has an absorption coefficient of 10 to the power 4 to 10 to the power 5. So what does it mean? Absorption coefficient very high. So that means in a very small thickness, it can absorb a lot of light. So in a small thickness, it can absorb a lot of light. So that is the advantage, is that you need less material to make this solar cell. For silicon solar cell, absorption coefficient is not as high as perovskite. So you need a large amount of initial material, raw material to make this thing. But here, the small amount of material, smaller thickness can do the same job. And also, these types of semiconductor-based solar cell, perovskite semiconductor-based solar cell fabrication is very easy. You don't need a very high temperature like silicon. If you want to establish a silicon solar cell lab in your institute, there's a lot of other requirements is there. You need to have a high temperature, 3000 degrees centigrade. But perovskite, no, room temperature. And you get a very high efficiency, 25%. And the other thing is that the band gap of this semiconductor is completely tunable. That means for silicon, the band gap is 1.1 electron volt. But for this particular semiconductor, the band gap can goes from 1.2 electron volt to all the way to 2.4 electron volt. Now, here is the role of AI and ML. So now, you see that, so basically, as I just mentioned in the beginning, see, AI and ML is just a technique. So you can apply it to energy photovoltaics field, you can apply to medical things, you can use for the drug discovery, you can apply it for prediction of some things. You can name anything and you can use AI and ML, basically. So nowadays it becomes like a buzzword, or everything, we sometimes joke that if anything does not have an AI ML, that is not complete. So that is something. So now, but what is the important role of the AI Now, what is the role of the what is the role of AI and ML in this particular case? I have already set up the background here. The role is that now, if you have studied the periodic table, you know that how many divalent cations are there. If I ask this simple question, I mean, everybody have seen a periodic table, right? In our class 8 standard or 9 standard. So if you look after a periodic table, basically we know that there are lots of divalent metals are there, right? You can name it, it can be lead, germanium, antimony, it can be bismuth or any indium and gallium. It can be anything. Okay. Now, at the same time, those of you who have a knowledge of the organic chemistry, you know that in the aromatic group, how many different combination you can do. In the aliphatic chemistry, how many different combination you can do. So if it is an organic cation, so how many different combination you can make, right? Similarly, this halide, you can have a chlorine, you can have a bromine, you can have an iodine, and you can have a mix of chlorine bromine or mix of chlorine iodine, bromine iodine, or chlorine bromine, like this. All of these combinations will give a new types of perovskite. Now, out of all of these, some are good, some are not good. Now, how do I know, which are good or which are not good, basically? So should I, if we make this combination and permutation, for example, if I take 8 or 10 different types of metal cations, and if I take 50 organic different cations, and if I take 3 metal, 3 halide anions, so you can see that probably I can make a million combinations out of that. Now, if I have an experimental data, I mean, at least something, so then I know some basic information about these elements. So then I will have, let's say 10 lakh different combination of this semiconductor, particular semiconductor, which will satisfy this ABX3 crystal structure. Now, as an experimentalist or as a material engineers, should I make 10 lakh material in the lab and test their individual properties, or make a device out of that and make their photovoltaic properties, test their photovoltaic properties? That is impossible. So that's what the role of the AI and ML comes. If you look at the most of the paper on the AI and ML in this particular photovoltaic technology field, whether I mean, I also suggest you to read. We have a very nice review how the AI and ML field. There are 2 reviews is there. One is that this AI, how the AI and ML can be utilized for for the emergent photovoltaic technologies. So the technique is whether you do the neural network or whether you do the inverse design problems, technique is well established. I mean, there are very less people who writes the new code. It's just just flipping the coins here and there. But one has to have a deeper understanding about the materials. If it is a photovoltaic devices, about the properties of the materials, about the electrical properties, of the optical properties, what are the input parameters which you are going to change? That will give you the accuracy in your confidence. That will give you R square value. You will have a good R square value for that. So in your final, when you do the your efficiency or all calculations for your AI, calculations and all these things. So we had a very nice review on Journal of Energy Chemistry on how to use the different AI and ML tool and what will be the step-by-step approach for photovoltaic technology. So they are we have published couple of many other papers also in this related. So the point is what I wanted to bring your attention here. See, now we need to understand that if we go from tin to lead, so as I mentioned that there are 10 lakh combination. So now what I will do, I will take these 10 lakh photovoltaic materials as my input materials. And out of the 10 lakh materials, probably I will shortlist some of the materials. That is my boundary condition. I'll shortlist some materials which I will want to run in my code, so that finally my output will be only 10. My test material, if I take an 80-20% separation or 70-30% division, so my testing material should be 10-20% or 30%. So that finally will give me 4 or 5 best candidates to synthesize in the lab or to do a test on that. So a simple example, when I change from the I make a ABX3 perovskite, I give this this basic problem to solve using AI and ML. We have to write an AI and ML code and to solve this problem you have all this tin-based perovskite and you have all this lead-based perovskite. Okay, one is called the lead-based perovskite, another is the lead-free perovskite. Now, what are the what is the best material you want to make out of that? So now, what first I have to do is that, between tin and lead, there's a significant difference between the electronegativity. There's a significant difference between the dielectric constant, right? There's a significant difference between the electron affinity of these two metals. There's a significant difference between the electronic radius of this, like ionic radius, not electronic radius, the ionic radius. There's a significant difference in the bond length. So these 5-6 things is my input parameters. Okay. And then, that is my one input parameter. Then when I put the halides along with that, I can put chlorine, bromine, or iodine. My electronegativity difference will be changing. So that is my, another input parameters. Similarly, if I change my, organic cations, so my these 5 properties will also be changed. So then, and another properties is that the band gap. If we change the band gap also, then also all of these properties will be changing. So we also have a paper, based on the band gap, how you can predict using AI technology, what will be the best photovoltaic materials. So now you put all these parameters as an input materials, and then, you put it in your, whatever the, in AI or ML code you are using, that doesn't matter. You just use 4 or 5 different techniques, which is best suited for you. And then you will see that you will be able to shortlist few materials out of this lead and tin. So, which actually will be fabricating in the lab. And for your kind informations, sometimes for doing this type of AI and ML calculation, next question you might ask, where I will get all this data? Where I will get, because you need the data, in AI and ML, data is everything. So you need the data. Where I will get the data? So should I dig the publication, thousands of publication and then tabulate the data, experimental data? No. Just to help the people, recently, the internationally, lots of scientists who are working on this particular photovoltaic field, they came together and they made a very nice database. It is called perovskite database. Search in the Google perovskite database. So this is a project which have been taken by 10 to 15 countries and by 15 to 20 research institutions, including some big institutions like MIT, Harvard, Oxford, NTU, etc. And they have collected all the experimental data of all the different types of these semiconductors, perovskite semiconductors. Just like you have a material database, just you have a Cambridge material database for for some other inorganic semiconductor, which is very, very helpful if you want to do a material study using AI and ML. Similarly, for the photovoltaics technology, there's a perovskite material database. So that is available free of cost to download all the data. So there are almost more than 56,000 material has been listed there with all the properties of this material, with all the optical and electrical properties of the material. And you can take certain properties based on your problem statement. Of course, what first we need to define the problem statement. What are you looking for? The stability of what the problem we want to solve in AI. And again, I want to emphasize AI and ML is a tool. You can use it for different problems to solve it. Your input is will be different. Your output will be different. But first we need to define what problem we need to solve. So that is most important thing. Okay, so I think this perovskite database project programs, where we are also one of the participants. There's a huge number of databases there, which is very, very useful for somebody who is interested to work in this field to download it and then to use your AI or ML tool to predict the best photovoltaic emergent material which you can readily make into the photovoltaic devices. Somehow my screen is not moving. Okay, so now it's moving. So now the next thing is that the crystal structure. I already mentioned about the crystal structure, and I have already spent a lot of time. And when I said that, I told you also to imagine in 3-dimensional, there is a giant crystal structure is there. And then you make a cube octahedral volume. So this is basically a cube octahedral volume. So here you see the octahedra, they are sharing their corner. And once they share their corner, so then you make a gigantic structure. And this is the uniqueness of the perovskite crystal structure, this gigantic structure. So which make these things. One more things one more constant, which we call as a tolerance factor, which tells that whether a particular semiconductor, you can call it as a perovskite or not. So see, I must mention that although I am talking about the perovskite solar cell, but perovskite is a very age-old material. barium titanate, lithium niobate. So these are like oxide-based perovskite. I am talking about the chloride halide-based perovskite, chlorine, bromine, iodine. But this oxide-based perovskite, so they are there for a long time, and it has been used for different applications, energy storage application, supercapacitor applications, memory applications. This material has been used for a long time. And again, these are the oxide perovskite. They also have their own band gap, but that band gap is not tunable, of course, unlike halide perovskite. But they have their own band gap, they have their own optical properties, they have their electrical properties. But they have, once you look at their crystal structure, and you have all these known parameters of the optical electrical properties, then again, in that case also, whether you want to make a supercapacitor or you want to make memory devices, RAM or PRAM devices. So again, you can use the same algorithm which I just explained to use or predict this kind of structure. But now we are talking about the perovskite, that is halide-based perovskites. So that's why, to distinguish it from the oxide-based perovskite, sometimes we call it as hybrid oxide hybrid halide perovskites. Hybrid halide perovskites. Now, for this case of hybrid halide perovskite, there is a formula is there. So this formula actually, it takes the atomic radius of the consisting atoms which make your perovskites. So based on that, for example, the tolerance factor T is defined as the radius of the A cation in the ABX3 or ABO3 plus RO for an oxide perovskite. It will be Rx for an halide perovskite divided by square root of RB plus RO. Okay. So now if the value of the T is between 0.89 to 1, then you call it as an oxide perovskite. And if it is 0.85 to 1.11, then it is halide perovskites. Okay. So the first three-dimensional halide perovskite which was reported in the literature was by replacing this CSPbX3. Here you see this is another perovskite crystal structure, and it satisfies ABX3, where B is this lead, X is this can be chlorine, bromine, iodine, and A is the cesium, is the organic cation. But now this organic cation, you can replace cesium with any of the organic cations, for example, methyl ammonium. Okay, CH3NH3 plus, then you call it as a CH3NH3 plus lead iodide. This is the atypical perovskite, which has a direct band gap of 1.55 electron volt, and this has been widely utilized for making solar cell photovoltaic devices in the industry also. Now, this is a typical structure of a organic, inorganic halide perovskites materials. You can see that the organic cations are sitting at the center of this cage, and then at the corner of this octahedra, you have this halide, and then at the face, you have this, the lead. The body in each of these body center, you have the lead cation. Okay, so the similar structure in a cross-sectional view. And then the other important parameters which I want to mention is the band gap tuning. So this is one of the unique things why, lot of papers, a lot of research work on the AI and ML is dedicated on the band gap tuning of these photovoltaic materials. So in this particular semiconductor, the band gaps, you all know, about the origin of the band gap. You might have read a lot of theory if you have studied some kind of solid state physics, you know that there are different types of theory, in physics or in chemistry for bond things, right? There are linear combination of atomic orbital. There are you can have chronic penny model. You have tight bonding model. There are so many more things are there. But fundamentally, where the band gaps comes from? Band gaps comes from the difference between the two energy level which have been spatially separated by some kind of energy. Now, in the perovskite, although it's like a composite semiconductor, so there the band gap only comes from this MX3 part or BX3 part. And by changing this X, halogen, chlorine, bromine, iodine, you can tune the band gap. For example, from 1.55 to 1.17. And even you can change it to 2.24 or 2.55 also by changing these things. Now, what is the implication of that? Why I say it's a remarkable? Because everything is related to the band gap. If your band gap is changing, your optical absorption is changing. If your optical absorption is changing, your photoluminescence is changing. I want to make an LED. So the same material, the same halide perovskite material, I can make a blue LED, green LED, or red LED. That means I can make a white LED by simply changing the band gap, which is not possible for any material so far. So that is the uniqueness. Okay, I want to make like a solar cell which will be able to absorb in the visible range and also like in the UV range and the near eye range. I simply tune the band gap. So then I can get a absorb like different absorption at different length. So that is possible in the case of the same material in the perovskite. So that is the uniqueness of this material. I want to make a laser out of it. I can do that things. But again, like whether you want to make a laser or solar cells or like I mean or like LED. But although today's talk is mainly focused on the renewable materials, like renewable technology. So for example, let's concentrate on the renewable technology only. So what you see that I mean the way you can change the M and X is like there is so many choices you can choose. As I said in the periodic table, M can be like lead, it can be tin, germanium, and all their like optical and electrical properties are already listed. So you take all these properties as input parameters, you change different X, you take their properties and input parameters, and you do your AI/ML coding. Like then you can generate different perovskite, different things, and all of them actually are new materials. So basically you are playing around with the materials. So much power you have right now has been given that you can just change the optical and electrical properties of the material by simply changing the compositions, the elemental compositions of the materials. Not only that, by changing the stoichiometry of the material also you can change the band gap. So that is the power of this particular photovoltaic technology and the power of the AI and ML in this particular technology. So this graph like nicely explains you what is the variations. This is a graph again. This has been a paper like I mean which have been published. This was like done by AI and ML technology in our lab, and then finally validated in our lab by fabricating all this material, and we fabricated all of these devices and all the experimental data that support our theoretical study. So I have a lot of other probably things to say, but I think I has informed Dr. Ravi earlier that basically I need to attend a very important meeting at 7 o'clock from the ministry. So I will just spend another 4 or 5 minutes, and then probably I will ask your forgiveness to. But I'll be available for over the email and the phone for any further discussion. So I just like to talk about one more couple of things which is very important, and I will share these slides with you. So so in IIT Roorkee, like we have like some of the milestone we have achieved is that we have achieved a the almost world record efficiency. I mean, of 20% in a three-dimensional perovskite solar cells and 21% in 2D, 3D heterojunction solar cell in a large scale. And we are also the first people who developed a solar glass. Solar glass means like we have developed a solar cell which is transparent. You can install it in a window or facade, and you can still generate power out of that. And basically that achievement was done by a continuous support of the AI, ML, and the photovoltaic technology group. Although I don't talk too much about the details of the AI, I just give you a background of how AI and ML technology is there. But we have in our group, we have a dedicated team is also working on the different types of AI and ML technology. But here, being in IIT, like, my focus is mostly to come across with the new algorithm of the AI and ML, like, which will reduce the, like, computing time, or which can address, like, some complicated problems in this particular field, rather than like just inputting your data and then you follow some neural network algorithm, or like random tree, random forest, or something like that, and you do this thing that we routinely we do. But our major activity is still going on the experimental part also, like 30 to 70%. 30% is the theory, 70% is going on the experiment part, where we fabricate, we make the materials, we test all their properties, and then we fabricate the devices in a small scale and large scale. And we also believe, and that this message I want to convey, that like this is very, very important, that what we are doing in whatever capacity we are doing in the lab, it is very, very important that should come to the market, that should be useful for the society. So with this intention, we have also started a startup mainly initiated by our student who have been graduated, and where we are manufacturing these low-cost solar panels, which will be helpful. And again, I tell you, like this team has a very dedicated and strong support from the theory group, AI and ML group, as well as the experimental group. And yeah, so if you are interested to utilize any of our facilities, if any of you, we'll be very happy to welcome with you. Like, we have all types of facilities, as I mentioned you, for starting from a world-class globe box for device fabrication to, like, UV visible fluorescence microscope, and then transient absorption, impedance, all types of, like, this is a very sophisticated techniques. And of course, like, some good clusters. And we have this Param Ganga also. This is a supercomputer where we do, like, things like density functional theory and like large, when you have many molecules, like, then Monte Carlo also. And also, like, we have the team, like, which works on the, as I mentioned, that new technology of the AI and ML. With this, I like to conclude here. And maybe if you have any questions, I like to address those questions now, or if time does not permit, we can I can also take it over the phone. So once again, thank you. Maybe I just conclude here, and thank you very much for your time and kind attention.
Thank you, sir. Participants, if you have any queries, you can turn on your, you can ask.
I hope that I have been able to convey some message, like, to the faculties, and maybe it will be useful. I mean, you can, if you have any questions, anybody, yeah, somebody has any questions, yeah, I mean, you can ask, or any comments also. If you have any comments or any observations, like, so then also you can please inform.
Sir, I have a question.
Yeah, please.
Sir, and the multi-stacked material, I mean, how many stacks that solar cell will have? I mean, is there any limitation on that number of stacks?
Yeah, it's good question. So basically, when you have a multi-stack material, basically, what I mean, like, the perovskite is a multi-component devices, right? So you have an anode and cathode, and then you have this active layer. In the case of perovskite solar cell, it is perovskite material. But to facilitate this charge extraction, we put multiple layers in between. For example, we want electron to go in one side and hole to go on other side. So we put a material layer in between, like, anode and the perovskite, or cathode of the perovskite, which will selectively pass electron and block the hole. So there is, as such, no limit. Usually, like, there are 7 to 8 materials layer has been put in to make these devices. But as such, there is no limit unless until, like, you block the charge. The limit is dictated by the carrier diffusion length. It should not be very, very, like, we cannot put n number of layers, like, we cannot put 10 layers, 20 layers, so that, like, charge extraction is prohibited, instead of, like, facilitating this. Our purpose is to extract the charge carrier in a better way to the electrode, so that we get a better current in the electric circuit. That is of a individual solar cell devices. Now, when you make a multiple devices, if your question is that multiple stacking is there, so yeah, that is also a very important area. So for example, people are making multiple stack perovskite tandem. So far we have been, we and the world community, they have been able to successfully, like, stack 3 different perovskite solar cell device together to make a multi-stack devices. Beyond that, it is very, very difficult because of the band gap matching condition.
Thank you, sir. Thank you.
Yeah.
Any more? Only 1 or 2 questions, sir. If anybody, you can ask, because
yeah, any question, like, any question, any comment, that will be or if you, and I also say you that, Dr. Ravi has my contact details, like, you can contact him if you want to use. We want to utilize this facility, like, I have developed these big facilities here. So if you want to utilize any facilities, or like, if you want to come either in AI ML technology or in experimental things, we are open, very much open to all of you.
So very good evening to you.
Hello.
I'm Ravinder.
Yes, please go ahead.
Thank you for your presentation. It's wonderful.
Thank you.
I would like to ask you one question. I'm sorry, it should not be commercial. But right now, if I want to go for an industrial setup, like an institution, over that there is a terrace. So what kind of the technology I should adopt? Because right now there are too many type of photovoltaic cells are available. People are coming with the different technologies. So I'm having almost 1 lakh SFT area. So is it really advisable to go for the photovoltaic cells with the panels, or as you mentioned, I can carry like flexible photovoltaic cells, which can be unrolled and which can be placed anywhere, wherever I can do that.
Okay. So yeah, Dr. Ravinder, is you have what you have asked, this is, see, there are two parts into it. One is that, of course, the first part of your question is that if you want to make a modular panel, you need a cell. So you cannot go panel without cells. And as I mentioned that we have to manufacture cells before going to the big module, because cell will be assembled to the module. But the second part of question is very interesting, about the flexible solar cells. Yes. So there are certain applications where you have a better demand of the flexible solar module than the rigid panel. For example, if you wanted to work for the defense sector, in the military, for example, in the space stations, for example, where space is a very, very constant, there the flexible solar panel is very, very useful. But when you go for the utility scale, for example, large scale grid connected electricity development, then still rigid solar panel is a better option than the flexible solar panel because of various reasons. First of all, for the mechanical mechanical steadiness, and second thing is that the cost of production of the flexible solar panel is much higher than your rigid solar panel. For in the utility scale application or grid scale applications, it will be not very beneficial to go to the flexible solar panel unless until the cost comes significantly lower as the rigid solar panel. But there are some niche applications, for example, like defense application, there are space applications, as I mentioned you, and then or medical applications, sensor, IoT sensor application, where you need more flexible things. So it is actually the end users, is the applications which will determine whether I should go to the flexible or rigid cells. But still, one comments to make that still making flexible solar cell is more challenging than a rigid solar cells. So that is also, and very costly also. So that is also a practical challenges which you need to work on.
That's a great, thank you, sir. But man, what will the cost difference, if you don't mind, if you have any figure like by percentage or something in comparison with the fixed frame versus the flexible photovoltaic cells? An approximate cost difference, maybe 60% is better, more than there is a fixed frames like that.
Sorry, I did not be able to hear you.
When I make a cost comparison between the fixed photovoltaic frames, then flexible photovoltaic cells, what difference I can notice percentage wise?
The efficiency wise, there is a lots of differences there. The rigid cells, shows an efficiency of for example, silicon. It's very difficult to make a flexible silicon. You don't see a flexible silicon. When the flexibility is there, you see flexible organic solar cells, or you see flexible amorphous solar cells. You can see flexible perovskite solar cell is there, but the efficiency got down there. Once you go for the flexibility, so then there the fabrication processes, there are a lot of changes happens. So then this is a very simple things, when the charge transport happens in a plane versus in a twisted plane. So then your mobility changes a lot, right? So then if your mobility changes a lot, then your carrier conductivity will change a lot. So less amount of charge carrier will release, will reach to the surface. So that is one of the problem. So that's why the efficiency of the flexible panel is less than the rigid panel.
Thank you very much for the technical explanation, sir. Thank you.
Yeah, no problem.
Good evening, sir.
Yeah.
Sir, the session was very informative. I have one question. How do you take into account the environmental impact of this lead in perovskites?
It is very good question, and thank you for asking this. So basically, this is in the beginning days of the perovskite research, it was one of the challenge how we can talk about the environmental impact of the perovskite. So the environmental factors like changes of the temperature, humidity, they can degrade the perovskite solar cells. So initially and last few years, a significant amount of research, and still now a significant amount of research is going on how to improve the environmental degradations of the solar cells. Now it has also been found out that the environmental degradation is one fact, but this material sometimes shows intrinsic stability, intrinsic instability. That has to be also addressed. But thanks to the lot of work on the encapsulation technology, for example, for silicon solar cell, we use EVA, a particular polymer for encapsulations. Now, there are a lot of work has been done in the last decade on this encapsulation technology. Now, the perovskite solar panel is completely encapsulated by using high molecular weight polymer, just like an EVA polymer, which stop the degress or ingress of any kind of water vapor, or there are different type of thermoplastic polymer also is used as an encapsulation, which prevents them for temperature variations also. So that helps to improve the environmental stability of the perovskite solar cell. But this is still, again, this is still an area where a lot has to be done. A lot of people are working on this area. Environmental stability of this perovskite solar cell.
Thank you, sir. Thank you, sir.
Okay.
Yes, sir. One question in chat box is there. Sir, how feasible this AI technology in solar cell simulation? What is the trade-off expected in real time?
Is very feasible. As I mentioned, that is very feasible. This is see, now that it is the time of photovoltaic 4.0 where we are doing automated fabrications. So basically, the next stage is that a robotic fabrications. And then this robotic automated fabrications, it has been coupled with the AI and ML technology. As I mentioned, we have also, you can search our Google profile, Google Scholar profile. You see a lot of paper we have published on AI and ML for the photovoltaic, and we have backed up by the experimental data also. So whatever the prediction has been made using the AI and ML, that experimentally it has been also found it isn't feasible. And I think this is the future. One has to use the AI and ML technology to address the various properties of this material, so that you come across what is the best photovoltaic materials, which is the best photovoltaic devices out of that.
Yes, sir. That's all the questions from the participants. Thank you so much, sir. First of all, I'd like to thank you because you have a busy schedule, but even though you accepted my request, thank you once again from bottom of my heart and from our institution side. Thank you so much. And also, I am going through that from the starting session onwards. I am going through your session also. It's very informative, because in chat box also everybody they are giving that their feedback is in excellent way. But you are giving the challenges, you are giving that how AI tool will be useful for perovskite photovoltaic, that type of devices. It's a very nice and informative, and you are giving challenges also. So once again, thank you so much, sir. I will be in touch with you. Thank you. Thank you, sir. I will meet you.
Thank you very much. Thanks. Thank you very much. And
thank you, sir.
Okay.
Thank you, sir.
Yeah, dear participants, the next session will be start at sharp 7:30. The second speaker will be joined soon. So sharp at 7:30. It will be closed at sharp at 9 o'clock. Please hold on.
Yeah, but please join with your registered name in Zoom. Please, everybody. Sir, you can also announce once.
Yeah, Still, for giving the attendance, I told you yesterday also, we are cross verifying from the Zoom attendance as well as from your feedback. But in feedback, you are giving separate name, and also even in your register portal, you are giving separate name. So please correlate that these two names should be same. Yeah, whatever you registered in the portal, in AICTE portal, the same name, with the same name we have to give the feedback. And also in joining name also should be the same name. Please keep in mind, please do the needful so that we can do